Hey everyone, so in this video we're going to start looking at what the inverse of a matrix is. And the idea here is not to teach you the techniques of how matrix inversion is done, that will be done in a different video, but just to give you an overview of what the idea of a matrix inverse is, because this is one of the most important topics in matrices and linear algebra, and especially if you do advanced degrees in mathematics and so on, then matrix inverse is one of those problems that even today mathematics researchers work on. So starting with a simple matrix 1 0 1 1 A, I'm calling that A, it's a 2 by 2 matrix. Then you define A inverse, right, and it's written as A minus 1 as a superscript. So it's A inverse, and that's this matrix that you see here, right? And why is it called the inverse of a matrix? Well, simple. Let's just take A and multiply that by A inverse and see what you get. So I take 1 0 0 1 0 1 1 and multiply that with the inverse, and I'm just showing you the steps here, and you've seen the video on matrix multiplication hopefully, and so you can already do this. So take a piece of paper, try it out, and you see that what you end up with is the identity matrix, right? And you're familiar hopefully with an identity matrix. It's a matrix where all the off diagonal elements are 0 and all the elements on the diagonal are 1. So you get that. And an identity matrix, when you do matrix algebra, which means it's the addition, subtraction, solving matrix equations and so on, the identity matrix effectively functions as the number 1 would do if you have just one variable and you do algebra and that. So you've seen that A times A inverse is the identity matrix. What if you do A inverse times A? Well, try it out, that's the next step, and you end up with the same thing. So you see, and it's important to note these assumptions, that for square matrices, so the concept of an inverse is not defined if the matrix is not square. But for a square matrix, which means the number of rows is equal to the number of columns, a matrix A has an inverse A inverse if A times A inverse gives you the identity matrix. Or a better way to put it is, the inverse of the matrix is the matrix which, when multiplied by the matrix itself, so when you multiply A by A inverse, either before or after, you get the identity matrix. Okay. So that's just the rule described again. For a matrix A inverse is the matrix where A inverse A is I, A inverse is I, right? Okay, excellent. So for a rectangular matrix, the reason this does not exist is because in a rectangular matrix, right, when you multiply a matrix and it's rectangular, right, you know that AB is not equal to BA. So this whole idea of A inverse A and A inverse could not be the same. And that's just a very simple explanation based on some of the matrix videos I've shown you before. But just with this itself, you can see clearly how, it's not possible to compute an inverse for a rectangular matrix. And I'm not going into a formal definition here, but this should just quickly give you an idea of why that's the case. It's just an example of why that's the case. Okay. Now, for a matrix A inverse, if it exists, and we'll see later that it need not exist for a square matrix, but if it exists, then that inverse is unique, which means there can only be one A inverse for an A. So how do we prove that? And the reason I show you this proof here is because it's important for you to remember this, and it's something that shows up actually in a lot of tests at the high school level. So, so let's assume that the inverse is not unique, and both matrix B and matrix C are both the inverse of A, right? So by definition, if you have two things that are the inverse of A, then A is not unique, is what we're saying. So we define B as A inverse. We say C is also A inverse, right? And just for reference, I'm calling this point 1. Now we know that for a matrix, A inverse A is the identity matrix, A inverse is the identity matrix. And we know, right, we've just said right now that A inverse can be B and A inverse can be C. So we know that AB is equal to BA is I, because if you just replace A inverse by B, you get that, right? Similarly, AC equal to CA equal to I, right? Simple, because we know B is A inverse and C is A inverse. So now what we do is we start, and this is an approach that is used a lot to try and prove different properties of matrices. Let's just start with matrix C, right, which is the inverse of A, so it's A inverse. We say C Now we know that a matrix multiplied by the identity matrix is the matrix itself. So we're going to say C is equal to Ci because we've multiplied it by the identity matrix of the same size, right? It has the same number of rows and columns as C. So what you get is C itself, right? So now we know that I can be written as AB, right? If you look at this step, we've seen that I is AB. And you're seeing that we've deliberately, instead of using AC, we're using AB here because we know B is also an inverse of A, right? So AB. So we write that as C, AB because we know AB is I. Okay. Now what you can do, and if you followed the video on the properties of matrix multiplication, or if you're familiar with the properties of matrix multiplication, you know that matrix multiplication is associative, right? So if you have three matrices, you can multiply them in any you can change the order of multiplication, and by that I don't mean you can multiply C with B. You can either multiply CA first and then multiply the product of that with B, or you can multiply AB first and then multiply C with that. So we're just going to change the order using the fact that matrix multiplication is associative, and say CA times B. But now we've just defined here that CA is I, right? CA is also, because C is also the inverse of A, so that becomes B. So we have started with C, and through these steps we have said C is equal to Ci is equal to Cab equal to Cab, which is equal to B, which means C is equal to B. So B is A inverse, C is A inverse, and C equal to B, which means the inverse is unique, right? The two things that we said could be different cannot be. B and C are the same, and so the inverse is unique. So that's something to always keep in mind, right? Okay. There's another property that we're just going to show you. Again, this is an important property at the high school level. It comes up quite a bit, which is that if you take the product of two matrices A, B, and you assume A and B are both square, take the inverse of that. That can be written as B inverse A inverse. Now, why do I say A and B are square? Because otherwise B inverse and A inverse don't exist, right? Okay. So take two square matrices A and B, where AB, the product, is defined. Then AB inverse, right? So the AB is the product. Let's say the inverse of that is AB inverse. So it's like saying C is equal to AB. So C inverse is AB inverse. It's the overall inverse of the product of these two. You take the product of these two, then invert it. Now again, like we've done in the previous step, you can, in the previous concept where we tried and proved that the inverse is unique. You see here, you take AB inverse, multiply that by AB, and you get the identity matrix, right? Because AB inverse is the inverse of AB. So by definition of the inverse, we know it's the identity matrix. So what we do next is multiply or pre-multiply both sides of that equation by A inverse, right? So A inverse times AB inverse is equal to A inverse I, right? It's like a simple equation with just, a simple linear equation that you've seen before, where you can multiply the entire equation by a scalar. Here it's with matrices, but it's the same principle, right? So A inverse times this. Now, as you can imagine, what you can do is open the brackets up for this using the fact that matrix multiplication is associative, and you can see here there's an A inverse A. So you get A inverse A, B, AB inverse is A inverse. We know this is the identity matrix, right? A matrix times its inverse is the identity matrix. So what we get is IB, because the identity, AB inverse is A inverse. Now what's the next step, right? Think about it. Well, you want to try and take this out, right? So multiply this by B inverse. So B inverse, I is gone because it's the identity matrix. It doesn't matter. IB is B itself. Pre-multiply by B inverse, and you get B inverse B times AB inverse, and now you've pre-multiplied this also by B inverse. Now we know B inverse B is also the identity matrix. You already know the reason why. A matrix multiplied by its inverse is the identity, and an identity matrix can be taken away because the identity times AB inverse is AB inverse. So you've got AB inverse is equal to B inverse A inverse, which is what we've proved. So you realize that if you take a product of two matrices, if that product exists, then the inverse of that can be found by taking the inverse of the second matrix B inverse and multiplying that by the inverse of A inverse. Okay, so these are a couple of properties of inverse that will be useful to you. Okay, so now how is the inverse actually computed, right? I've been talking about matrix inverse. So at the high school level, the two approaches you learn, one is elementary row or column operations, right? And there's a completely separate video on how you use this how to use elementary row and column operations to compute the inverse. And there's another video on elementary row and column operations, but basically by adding and subtracting the rows of the matrix from each other, you can actually compute its inverse, right? And at the school level you do it by hand for simple 2 by 2, 3 by 3 matrices. At the advanced level, this gets coded up into an algorithm, and that's how it gets done. The other approach is by using determinants and matrix adjoints, right? And this is another approach that we have discussed in detail in the video on determinants and adjoints. So these are the two approaches you will see on how to convert the inverse of a matrix. So now that I've told you about the two approaches that you will see at this level, now for a 2 by 2 matrix, there is a simple formula that comes about from the determinant approach to computing a matrix inverse. So if you take a 2 by 2 matrix, and these are just general variables, right? So you can use any general symbols. So you can use any term in this. This could be 1, 1, minus 1, 1, or so on. But for a general matrix A, B, C, D, the inverse, A inverse, can be written as 1 by AD, right, which is this, minus BC, times, and then if you see the rows and columns have been, the order has been changed, so it's become D minus B minus CA. This is the inverse of this matrix, right? And this, you'll see how this comes about in the video on computing inverse using determinants. The other thing you see here is if this term is 0, then this is not defined, because you'd be doing a 1 by 0, which is not defined. And this term is the determinant of this 2 by 2 matrix, right? So this is the determinant, and you will learn more about determinants in the video on determinants. But this is the determinant, and if this is 0, then A inverse is not defined. So you do see that if, and this is for a 2 by 2 matrix, but this principle holds in general, right? That if a determinant is 0, then the matrix inverse is not defined. Okay. So we're talking about matrices where the determinant is not defined. Look at this matrix, right? 1, if you do AD minus BC, 1 minus 1, 1 into 1 minus 1 into 1 is 0. So this is a matrix that cannot be inverted. So matrix is singular. It's called a singular matrix if you cannot invert it, or if its inverse does not exist. And if and only if its determinant is 0, a matrix is singular. And in this case, you can see clearly the determinant is 1 times 1 minus 1 times 1, which is 0. For a 2 by 2 matrix, just take the product of these two and subtract that from the product of these two, and you get the determinant. So a few more examples, and in all these cases the determinant is 0, but this will help you quickly identify if it's a singular matrix or not. If a matrix has either 2 rows or 2 columns being the same, then you know it's singular, right? Because the determinant ends up being 0. So in this case, and you can try this out, look at this one, you've got these 2 rows, these 2 columns, or for that matter these 2 rows are the same, so you know that you can just look at that and say, okay, the determinant is going to be 0, so this matrix cannot be inverted. Another example is where if you have a row that's full of zeros, right? So 0, 0. Now you see here also that these are similar, but even if this was 1, 2, 0, 0, if a full row or a full column are zeros, then the determinant is 0. And so as a result of that, the matrix cannot be inverted, or it's singular. See, these are just 2 cases to help you identify quickly if a matrix is singular, right? So with this, hopefully you've got a fairly good idea or an introduction to what an inverse of a matrix is. You understand what a matrix inverse is. So to clarify this concept, please take a quick test on TeachYaar.com, and I've dropped a snapshot of that test here. So to take the test, you can scan the QR code, or we've dropped this link that you see here. That's a link to the test, and we've dropped that link in the description section and in the comment section. So feel free to click that and take the test. It's free, and it will give you a little more insight into what an inverse is. And of course, there are quite a few other videos describing how an inverse is computed, what inverse is used for, and so on. And please subscribe to the TeachYaar YouTube channel.